This is the 13th video in our series on topology, and in the previous couple videos we talked about connectedness, both in the real numbers, using a couple of different topologies, and in general. And today we want to look at another notion which is tied to connectedness, and that is path connectedness. But of course we're going to need a definition to get off the ground. So let's say we've got a topological space X, and we've got any 2 points inside of X. So a path between any of these points, so between X and Y in this case, is simply a continuous function from the unit interval to our topological space, so that f of 0 is X and f of 1 is Y. And then if we've got one of these paths between any 2 points in a topological space, we say our topological space is path connected. And here's a picture of that going on here. So here we've got X, here we've got Y, and here we've got this path going from X to Y. I'd like to point out here that this isn't a jump. Maybe it's just like the path going in front of or behind one of its strands along the way there. Okay, so let's look at a couple of examples and non-examples. So I think it's pretty clear to see that Rn is going to be path connected for all natural numbers n. So that means the real numbers is path connected, R2 is path connected, R3 is path connected, and so on and so forth. And well, we can see that, obviously intuitively, but we can also see it just by taking a parameterized line segment between any 2 points. So let's do that. So let's say we are given X and Y inside of Rn. So we're thinking about those as n tuples. Let's consider the function f that goes from 0, 1 to Rn. And let's say it's defined by f evaluated at t is equal to 1 minus t times x plus t times y. And now, well, let's note that f of 0 is pretty clearly equal to x because it zeroes out that y component, if you will. And we have f of 1 is equal to y. And also, this function is, well, I think it's pretty clearly continuous. You could maybe sketch some little proof of it being continuous like this. So notice here we've got our x, here we've got our y, and so our function, well, like I said, it's just this line segment right here. And if you take some sort of neighborhood inside of, well, R2 in this case, but Rn in general, that'll be something like this. So I'm not putting the dotted lines here, but let's just consider that as an open set. We'll call that open set V. But notice that that's going to intersect here and here along the line segment. But this spot on the line segment right here is going to correspond to something that we'll call maybe T0 in the interval from 0 to 1. And then this spot right here will correspond to T1. But with this construction, we see the pre-image of V is simply our open interval from T0 to T1. But that means that we've really waved our hands at it, but we've shown that a pre-image of an open set is open. But that's our continuity condition in this topology class. Okay, so now similar to this Rn being path connected, Sn is also path connected, where that's the n-dimensional sphere. And that's going to be for n bigger than or equal to 0. S0 is simply 2 points, and that's clearly not path connected. But let's see, if we've got n equals 1, we've got a circle. Again, that's pretty clearly path connected. We could take a point right here and a point right here and observe that there are 2 paths that go between these 2 points, kind of one through the northern hemisphere and one through the southern hemisphere. And then for the n equals 2 case, it's also path connected. For the n equals 3 case, well, in all of these, it will be path connected. And I'll sketch a proof of this as well. And this is going to involve the composition of what we did above with something called a stereographic projection. Now, I'll let you guys look up stereographic projection if you're not familiar with it, but the idea is this. So we could take a point maybe just between our point X and Y and consider this point as the northern hemisphere, sorry, the northern pole. And we'll use this northern pole as our point of stereographic projection. So what I mean by that is we're going to cut the sphere or the circle at the northern pole, kind of remove it, if you will, and then we're going to unfold it into a line in this case and a plane in that case, and so on and so forth. So if we remove the North Pole here and unfold this, what we'll have is a line. And well, it looks like we're going to have an open interval, but the stereographic projection, what it will do is extend that open interval into a whole line. But anyway, what we see here is that when we do this unraveling, our point right here that we took over here to be, for instance, X, and our point over here that we took to be equal to Y, unfold into those points, but then there's something clearly between those. And that's the kind of idea that you would do for all of these. So you would be given, you know, like we were over here, any point X and any point Y. You would take anything which was a third point, consider that as being the northern hemisphere, and then you would do your stereographic projection with respect to that northern hemisphere. And in that case, that's going to give us a plane, and X and Y will be in that plane, and then we can take the line segment between X and Y just like we did above. And every point in this sphere is represented in the plane except for the northern hemisphere, which we removed. That's the point at infinity, if you will. But let's recall that all we did is once we were given 2 points, we chose any third point to be the northern hemisphere. So we chose our 2 points to find a path between before we fixed our point that we're stereographically projecting off. And then, well, I guess the last thing that you would do is you would map this back up to the sphere and you would get a path between X and Y. Okay, so now let's look at some other examples. Okay, so for our next example, we'll look at the punctured Euclidean space Rn minus the origin. And this is going to break down into 2 cases. The first is the case when you're looking at the punctured line, the n equals 1 case. But let's observe in the n equals 1 case, that separates the real line into the interval minus infinity to 0 union the interval from 0 to infinity. But then that's not connected. But if it's not connected, it can't be path connected. And that's because we're about to prove that a path connected space is necessarily connected. But then you could also perhaps use like the intermediate value theorem to show that there is, for instance, no path from -1 to 1. Okay, so let's look at the n equals 2 and bigger case. So here I'll just put bigger than or equal to 2. And in this case, it is path connected, and that's because you can always bend around the origin. And so let's prove that. So let's say we're given X and Y in this punctured space, and we're going to break this into 2 cases. The first case is if X, Y, and 0 are not collinear. And so just as a brief picture here, let's say that means that X, for instance, is here, Y, for instance, is here, and then 0 will be down here. Not being collinear means that they do not lie on a single line. But now observe that here we can just take the line segment from X to Y, and well, since 0 is not collinear with X and Y, that means 0 will not be on that line segment, meaning that line segment is totally contained in our punctured space. And well, we can take the same parameterization of the line segment that we had before. So perhaps it would just simply be f of t equals 1 minus t times x plus t times y. Okay, so now we need to look at the second case, which is if x, y, and 0 are collinear. So let's maybe sketch that out over here. And that would be something like this, and then maybe 0 is in the middle, although I guess you could really separate this into a third case, which is where 0 is not in the middle of x and y, but we can put both of these together. And so the idea here is to pick a third point, which we would perhaps call z, and z is going to be necessarily outside of the line between 0 and y. So you can always find something outside of the line between 0x and y. And then what we'll do is just paste two line segments together. So it'll go something like this. So that'll be the line segment from x to y unioned with the line segment from, x to z and then z to y. And then by the gluing lemma, this will be continuous. But we could also write down a formula for it if we really wanted to. So let's say that f of t is equal to the following piecewise defined function. So it'll be x times 1 minus 2t, and then plus 2 times z times t. And this is if t is on the interval from 0 to 1/2. So let's observe that f of 0 will be equal to x based off of this. Notice that zeroes out the z part. And then z is going to be equal to f of 1/2. So if we plug 1/2 into here, it clearly zeroes out the x part. And then for the rest of it, we'll have z times 2 minus 2t plus, and then we'll have y times 2t minus 1. And this is if t is on the interval from 1/2 to 1. But notice our setup right there gives us y is equal to f of 1. And also, if we plug t equals 1/2 into this formula right here, we'll get z as well. So that's f of 1/2 for both of the pieces of f. But of course, we need that for this to be continuous. Okay, so anyway, by the gluing lemma, which we proved a while ago, this is a continuous function, which means we do have a path between x and y. Okay, so that's good. Now let's prove that result that I alluded to earlier, that path connected implies connected. So now we're going to prove, well, like I said, that classic result, that if x is path connected, then x is connected. Okay, so we're going to do this by way of contradiction, or I guess maybe it's also kind of by the contrapositive, but any way you want to look at it, by way of contradiction, let's suppose that x has a separation. And so if it's not connected, then it has a separation. And let's say that separation is via u union v. So I've put that dot there to mean disjoint union. And well, u and v are going to be non-empty open sets. Okay. So next, let's take x to be inside of u and y to be inside of v. So observe that means that x cannot be equal to y because x and y do not overlap. This is a disjoint union. Okay, and then also let's suppose we have a continuous map that is building a path from x to y. So it's going to be a continuous from 0, 1 to x, our topological space, such that we know that f of 0 is equal to x and f of 1 is equal to y. Now we want to show why that's some sort of issue. So let's look at this. So let's look at the set u intersected with the image of our whole interval here. And then let's union that with our set v intersected with the image of our whole interval there. And now, well, let's observe that this is equal to the image of our whole interval. Because it's the image of our whole interval, let's see, intersected with u union v, but u union v is equal to x. So it's like a subspace intersected with the whole space. So anyway, that's going to be the subspace. But then let's also note that this is a disjoint union, so I can put a little dot here, and it's a disjoint union because those clearly don't overlap, because U and V don't overlap. Let's also observe that both are non-empty. And we know both are non-empty because X is inside of this left one and Y is inside of that right one. Then let's also notice that they're both open in the subspace topology applied to this image. So, well, let's collect our data so far. We've got two sets that are open in our subspace topology. They are non-empty and they're disjoint and they union to the whole thing. But that means that we have a separation of, F, or the image of 0, 1 under F. So that means that the image of this is not connected. But I think we proved earlier, actually I know we proved earlier, that the continuous image of a connected set is connected. But that's exactly what we have here. We have the continuous image of a connected set, but assuming that we had this path in the first place, we see that that must be not connected, but clearly that's our contradiction. Okay, so now, well, what have we seen? Well, we saw some examples of path-connected and not path-connected sets, but all the examples that we've seen before were both path-connected and connected. Now, we just showed that path-connected implies connected. And then, since we've got this new definition of path-connected, there must be some examples of things that are connected but not path-connected. Otherwise, we wouldn't need this new definition. So let's go ahead and prove that we can find some things, or let's look at some examples of topological spaces that are connected but not path-connected. Okay, so for our first example of something that's connected but not path-connected, we're going to look at a really famous example, and that's the topologist's sine curve. So we're going to start with this set S, which is all ordered pairs x sine of 1 over x, as x ranges from 0 to 2 pi. Sorry, that should be 0 to 1 over 2 pi. And let's see, well, notice that it cannot be equal to 0 because we'd get a 0 in the denominator there. Then, well, let's sketch out what we have over there. So notice that if we plug in x equals 1 over 2 pi, that's going to flip up and give us sine of 2 pi, which is 0. So that's why it goes through the x-axis here. Then if we plug in 1 over 3 pi, the same thing. 4 pi, 5 pi, all the same thing. But let's notice that these reciprocals of integer values of pi, or integer multiples of pi, will get closer and closer and closer together as we get closer and closer to the origin. And we can just see that here. Notice that 1 over 5 pi is closer to 1 over 4 pi than 1 over 4 pi is to 1 over 3 pi. And this one right here, which is 1 over 6 pi, is even closer to its neighbors than the previous ones. And so that means that this function is just going to, for lack of a better term, wiggle faster and faster and faster as we go to the origin. And let's first start by looking at the closure of this, and we'll prove that the closure is simply the original set union with this thing right here. So it's the singleton 0 cross the interval from -1 to 1. But notice that that's just a bit along the y-axis, if you will, from -1 to 1. So that's that bit right there. So now that I've shaded that in there, I've got like a picture of my S bar. So now let's go ahead and prove that this is the closure. I guess we're not going to do all of the details of the proof. What we will do is show that this is the set of limit points. So let's take an arbitrary element from this. So let's say that's going to be of the form 0y. So that's in this 0 cross the interval, and show that this point is a limit point. Okay, so how do we show that it's a limit point? Well, we show that if we take a delta neighborhood of this point, it intersects the original set. Notice that we don't have to worry about it intersecting the original set minus this point, because this point is not within the original set. Okay, so let's also let delta be an arbitrary number which is bigger than 0. That'll be the thing that we form our delta neighborhood out of. Okay, so what's the first step? So let's find a value theta, and let's say this value is between 0 and 2 pi, such that if we take sine of theta, we get y. So sine is going to map this interval onto the interval from -1 to 1. That's how we know that this is possible. Okay, so next up, we're going to find a natural number, which I'll call capital N, satisfying the following rule. And that is that 1 over theta plus 2 pi times n is less than delta. So I think it's pretty clear you can do this. Delta is meant to be very small, but let's observe that this object right here, well, I guess we could argue this object right here is actually less than 1 over n. And then we can always find a 1 over n to sneak in underneath delta. Okay, so next up, let's set x equal to this thing that we right here created. So 1 over theta plus 2 pi times n. And let's note that if we take sine of 1 over x, that's going to be sine of theta plus 2 pi times n. But that's sine of theta, which is equal to y. That's by the 2 pi periodicity of the sine function. Okay, now next up, let's look at the distance, the Euclidean distance, between 2 points in question. The first point will be x comma sine of 1 over x, and the other point will be 0, y. And so what this is going to show is that this point right here, x comma sine 1 over x, is in the delta neighborhood centered at 0, y. But again, that's what we need for this 0, y to be a limit point. And I've just noticed that here, I'm not using my angle brackets or parentheses to mean an ordered pair, which we've been trying to do in this class. Okay, so anyway, let's do the calculation here, and just using Euclidean distance, it's going to be the square root of x minus 0 squared, so that's going to be x squared, and then sine of 1 over x minus y quantity squared. But notice sine of 1 over x is simply y, so that distance is 0, or sorry, that difference is 0. So we simply get the square root of x squared, which is equal to x, which is equal to 1 over theta plus 2 pi n, but that is less than delta. So let's see what we've shown here. We've shown that this point, x comma sine 1 over x, is inside of the ball of radius delta centered at 0, y. But again, what does it mean to be a limit point? It means that every neighborhood of that point intersects the set. But in this case, since we're in the Euclidean topology, we just need to look at every ball of radius delta centered at that point intersecting the set, which is just exactly what we've done, because this point is not only in that ball of radius delta, but it's also in S. So just as a bit of a conclusion, that means this point this point 0, y is a limit point of S. But that shows that everything in this set right here is a limit point of S. Now, of course, we would have to show that if we're outside of that set, we're not a limit point, but I'll maybe leave that for you, and I'll just say that this claim is proved. Okay, so now we've got our tools in place, and we can do our goal here, which is to show that this space is not path connected. Okay, so before we get started, let's note that earlier in my homework exercise, we proved that if y is connected, then the closure of y is also connected. But that means this closure of S is connected, just applying that result. Now we want to show that this closure of S is not path connected, and we're going to do this by way of contradiction. So let's, by way of contradiction, suppose we've got a function from 0, 1 to S bar that is a path between the origin and, well, a carefully chosen point on the S part. So kind of obviously here, we have to choose something from this set of limit points and find a path to S, because S by itself is pretty clearly path connected. You can just go along the curve. And then this interval is also path connected. So that being kept in mind, if we're going to show it's not path connected, well, you want to assume you've got a path from one of these components to the other component and show that something messes up. Okay, so such that f of 0 is equal to, let's take that to be the origin, and then let's say f of 1 is equal to the point, let's say maybe it is 1 over 2 pi comma 0. Although, to be honest, any point here would really work. But just to see what we've got going on here, we're assuming we've got a path from this point right here to the origin. Okay, great. But now let's notice that we can write f of t using component functions. So let's say those component functions are x of t and y of t. And then what do we know here? We know x of 0 is equal to 0. We know that x of 1 is equal to 1 over 2 pi. And then we know y of 0 is 0 and y of 1 is also 0. That's what it takes to have those starting and ending points over there that we talked about. And then let's also note that for t bigger than 0, f of t is on the curve part of our set. It is not on the interval part. And that's because, well, it's on the interval part just at the very end. Now, I guess you could argue that it might be on the interval part before that, but what you can do is just find the first place where our path is on the, for lack of a better term, interval part of our set, and then cut the path there into maybe a subpath, if you will. But anyway, we're not going to worry about that so much. We'll just say that for t bigger than 0, f of t is on the sine curve part, not the interval part. Okay, nice. But what does that tell us? That tells us that y of t is equal to the sine of 1 over x of t for all t on the interval from 0 to 1, not including 0. Again, because that's the condition we need to be on the s part, not the interval part. Okay, nice. Now we're going to use the continuity of our component function x. So we know this function x is continuous because f is continuous. And it's a component function that is building a continuous function. And what we'll use from the continuity is the intermediate value theorem. So let's use the intermediate value theorem to find some numbers. And those numbers are going to be t1. T1 is going to be less than 1, but T1 is going to be bigger than T2, which is going to be bigger than T3, so on and so forth. They're all going to be bigger than 0. And they're going to satisfy the following rule, that if you do x of t sub n, you'll get 2 over 2n plus 3 times pi. So again, we know that x takes on all of these values as our function goes from, let's see, the x value of 1 over 2 pi to the x value of 0. And that's because all of these values are between 0 and 1 over 2 pi, but the intermediate value theorem tells us that our function takes on all of those values. But now we'll see that this will immediately be a problem. Let's observe that sine evaluated at x of t sub n, which that's our y of t sub n by, let's see, this rule right here, is going to be equal to the sine of 2n plus 3 times pi over 2, which is equal to minus 1 to the n. So the sign of this is alternating between being plus 1 and minus 1. And now let's finish this off by looking at the limit as n goes to infinity of f of t sub n. So we know that this t sub n should be approaching 0. So that's by our construction. But since the t sub n is approaching 0 and f was assumed to be a continuous function, that means by the sequential version of continuity that this should also converge to something. Well, in fact, we know what it should converge to. It should converge to, let's see, this point 0, 0 here. But we'll see that that will not happen. And that's because this is, in fact, the limit as n goes to infinity of x of t sub n, y of t sub n, but that's going to be 2 over 2n plus 3 times pi, and then minus 1 to the n. Of course, that first coordinate does converge to 0, but the second coordinate does not converge to 0. So that means that this whole thing does not converge. I'll just put D and C there for does not converge. But that contradicts the continuity of our function f. But that contradicts our ability to get this path in the first place. All right, so now let's look at another example of one of these spaces that's connected but not path connected. So for our next example, we're going to look at the unit square, so 0, 1 cross 0, 1, in the so-called order topology. We haven't looked at the order topology yet, but this is a great application of it to show something's connected but not path connected. So what's the order in this order topology? Well, it orders ordered pairs, if you will, by a lexicographic or like a dictionary or alphabetical type order. So you want to think about it like this. If you've got two words, one starts with AB, the other starts with AC, the AB is before the AC. But in our case, we've only got two letters, the first entry and the second entry of the ordered pair. But we've got as many letters as we want, because our letters range over everything from 0 to 1, versus in alphabetical order, we only have 26 letters. But really the idea here is the same. So if we were to write that out, we've got our ordered pair AB is less than our ordered pair CD, if and only if the first letter A is less than the first letter C, or if they're equal, the B is less than D. So the second letter is less than the other second letter. So for example, a half comma 1 is less than 3/4 comma 1/4. So let's look at those on our picture. So let's see, 1/2 comma 1 would be like right here. So I'm color coding this. That's our yellow underline. And then 3/4 comma 1/4 is here. So let's see, yeah, this one is before this one. And that's because you can think about all of these as being like some sort of lines that are all wrapped together like that. That's another way of thinking about it. Okay, so let's look at this other one. A third is before a third 2/3. Now, this is maybe a little bit easier to see. So a third is perhaps right here, and then 1/3, 2/3 is like right here. So now notice that since we've got this total order, we can define intervals. And so, for example, if we looked at the following interval that has a starting point of AC and an ending point of BD, that's simply going to be everything between that starting point and that ending point. But actually, let's change our letters to be in line with what we had before. So AB to CD. So let's get a picture of this. So let's say maybe A is here. And then we'll say C is right here, but let's say maybe B is here and D is here. Okay, great. So let's see, our first point will be this point right here, AD, but it's not going to include AD. But notice it's going to include everything just above AD, because all of those are bigger than AB. But it's not going to include anything that's directly below AB. Now let's go over to our ending point CD. So that point's like right here. Now it's going to include things directly below CD because those are less in our order, but it will not include those things above CD because those are outside of the order. But let's notice that everything in that rectangle between will be in our interval because all of these points are between AB and CD in the order that we have right here. So we could shade it in like this. So that would be like a picture version, or a picture version of this interval, if you will. Okay, cool. So now that we've seen this nice order topology put on the unit square, let's see how we can use it to show that this space is connected but not path connected. All right, so now let's dive into the proof that it's connected but not path connected, but I'm going to cheat a little bit here. To show it's connected, I'm going to leave that as a homework exercise. This makes the unit square something called a linear continuum, and showing that a linear continuum is connected is essentially the same thing as showing that R is connected. And that's because if you've got a linear continuum, then essentially the basis for the topology is just open intervals, so it acts just like the real numbers. So all you have to do is write down a parallel proof that this is connected, well, a proof that's parallel to the proof that we did in one of our previous videos that R is connected. Then, well, also that follows for showing that this thing is Hausdorff as well, which I'll also leave as a homework exercise. Now let's show that it's not path connected, which is a little bit more technical. So by way of contradiction, let's suppose we've got a path from the origin to this point 1, 1. So it goes from the lower left corner to the upper right corner. But let's recall that this lower left element was the minimal element in the whole space, and this upper right element was the maximum element in the whole space. But since our path goes from the minimum to the maximum and it's continuous, by the intermediate value theorem, we know that F is surjective. So let's write that down. So by IVT, F is an onto map. So that means it hits everything inside of this square. Now, immediately that seems kind of suspicious because we're mapping the unit interval in a onto and continuous way to the unit square. But intrinsically, the unit interval and the unit square seem different. And I guess like the proof here that we're going to show will give some sort of evidence that they are different. Okay, so anyway, let's get to it. So now what we want to do is fix some point x, which is between 0 and 1. And it can be really any point between 0 and 1, including 0 and 1. And then we want to consider this set, which I'll call V sub x, which is going to be equal to the singleton x crossed with the open interval from 0 to 1. So let's see, V of x looks, or V sub x I should say, looks something like that. So let's write this down. This is our point x. But now let's notice that V of x is an interval in the order topology, and we could actually write down what interval it is. So notice it's the interval that goes from x comma 0 to x comma 1. But that tells us that it's definitely open. Okay, cool. So, but this set is open. We know that pre-images of open sets are open, so that tells us that the pre-image of V sub x, which we'll call U sub x, is open, and it's going to be open in the subspace topology on the closed interval from 0 to 1. Okay, nice. But now I want to make a following claim, and that is that we know that U sub x intersect U sub y is the empty set if x is not equal to y. So if we take some sort of other point here and construct the V sub y and then pull that back to the U sub y, we get a totally different set than what we started with. And then I guess we could show this pretty easily. So let's note that if we have a t inside of U sub x intersected with U sub y, then that means that f of t is inside of V sub x intersected with V sub y, just by our definition of U sub x. But we see that that's a problem, and that's because if we've got a different x and y value, let's say that this is the y value, then v sub x intersect v sub y cannot intersect because there are these totally different open line segments here. So anyway, that is empty. So we just proved that claim that u sub x intersected with u sub y is empty. Okay, so now let's see how we can use that. Okay, so we just did a construction that produced a collection of disjoint open sets u sub x, and those were open subsets of the interval from 0 to 1, and they were indexed also by the interval from 0 to 1. But since they're open, they must contain a rational point. I think we proved that earlier, that any open set of the real line contains a rational point. So let's choose some rational point, I'll call it q sub x, inside of u sub x, and I'll just put intersected with the rationals here to show that we're choosing a rational point. And we're going to do this for all x on the interval from 0 to 1. But let's notice that that has created an injective map, and that injective map takes x to q sub x. But notice that takes the interval 0 to 1 and injects it into the rational numbers. But that's problematic because we've got an uncountable set being injected or mapped 1 to 1 into a countable set, which we know is impossible. So there's our contradiction. So now, well, we finished this proof that this is not path connected. Okay, so now I'm going to leave you some other homework exercises in addition to these two right here that we talked about. Okay, so now I've got some exercises for you. The first is to show that if n is not equal to 1, then Rn and R are not homeomorphic. Now, keep in mind that this whole video was about path connectedness, so you probably want to use something about path connectedness for this proof. Now, next up, let's suppose we've got a countable subset of the plane, and our goal is to show that if we take R2 and subtract out those countably many points, we still have something that's path connected. And that's a good place to stop.